Alright guys, so last chapter of this insane summertime course. So I kind of gave a little preview of the idea behind this chapter. Here's what the distribution looked like. So let me do this. How many z-score formulas do we know now? I would say one, but there's several different iterations of the same idea, right? You guys go with me. So z could be this, z could be this, z can have s's in them, z could be with p's in it. Corn, no, I'm joking, it's peas. All right. Cool. But all of these relate to what picture. Eventually, in most of our problems, we have to know that it's what kind of thing that we're working with. We could do it. We could do it. What kind of distribution do we normally have to know? Yeah. So all these fall on this picture somewhere, right? And this picture is actually independent of these. I don't think I showed you the formula for this, and I'll spare you from that. There's a formula that if you plug it in your calculator, it'll come out with this shape. And it deals with e to the negative stuff. It's neat. It's funky-delic. If you know, anyway, I'm not going to tell what calculus. So, what we're about to do, and the discussion I had before to get you ready for this chapter was, what determines the shape of this? What determines whether it's going to be really skinny or really fat? Standard deviation. And this is how z-scores are distributed in a normal curve. And the shape is determined by these standard deviations. So now we're going into a section where, what if instead of plotting z-scores from samples and seeing what they look like, what if I plotted the standard deviations of samples and see what they look like? Bless you. I should not have any reason to expect the same shape to show up. That would be a little insane, right? Because the shape is determined by the freaking standard deviation for a situation. Now I'm going to plot a bunch of standard deviations from all the... So remember how we went to Florida? We didn't really go to Florida, in case you guys are like, what day was that? And we took samples and we saw that it became normal if I took a large enough sample size. Do you remember doing that? We took a sample and I plotted the mean. Took another sample, plotted the mean, and eventually it came out looking more normal once you were above 30. Are we okay with that? You guys remember that vaguely?
Was that the one with the kids and the adults?
Yes. So it was an alternate universe Florida where nobody was in the middle. Some weird Logan's Run where some people were just grandfathered in, so they could be up here, and then this group, kill them once they're a certain age. Nobody in the middle, right? You guys remember that? Okay, so now I'm doing the same thing. Instead of plotting sample means, I'm going to plot sample standard deviations. Every sample I take is going to have its own standard deviation, correct? Correct? Good. So it's going to end up, just to cut to the chase, and this is cutting to the chase, believe it or not. What is the smallest the standard deviation can be?
0.
0. I love it. Can't be negative. It's the square root of a squared thing. Can't be negative. But it can't be 0 if my data was what? What would make the standard deviation 0? If the data looked like what? Give me an example. What standard deviation of 0 mean? Because what's the standard deviation tell you about a set of data? Yeah, they're the same value. It tells you the spread, how spread out it gets away from its center on average, right? So the only way to be 0 standard deviation is if they're all the same data points. So if I went out and took a random sample of people and asked them their age, is it possible they're all the same age? Huh? No, okay.
Not likely, but it could happen.
Is it possible? That's all I'm asking.
Yeah.
Yes. I like it. And in fact, if you're really being honest, if we're on Grossman College, there's a really good chance that, you know, as long as it's not a crazy big sample, if I took a sample of 7 people, I'm not going to be totally freaked out if they all have the same age, to be honest. If they were all 19, now if they were all 70, then I might stop and wonder, what have I done? But obviously, we're at a community college. There's going to be a lot of students who come right out of high school. Not everybody. You guys semi with me? All that was on the side, but oh well. So it kind of makes sense. Z-scores go forever in both directions. Forever. These guys have a hard stop at 0. So here's what it looks like. Here's the basic look of it. This side goes on forever. Theoretically. Yeah. Skewed, I love it. Skewed to the
Right.
I love it. And I don't know if you guys remember, this was my Because he had his long ass tongue. Oh. You haven't seen Star Wars, I don't understand. Not the 90s ones. I mean the original ones. Alright. And maybe the ones. Anyway, so I will call this the Jabba the Hutt distribution. But it is officially the chi-square distribution. Just in case anyone's curious, this is a very interesting thing, and this actually gets at a deeper truth about where this shape comes from. If I took a normal curve and folded it on itself, you would actually get that shape for a certain sample size. That's all I'm going to say. That relates to why it's called chi-square. It's like squaring the z-scores amounts. Okay. All right. So most standard deviations of samples are going to be in here. Some of them are going to be very small, and then they could go really, really big. Because I could pick a sample of people and have one 1-year-old and a bunch of 90-year-olds. That's going to be a huge standard deviation. All right, let me stop for a second. So this picture exists independent of this shit. These are just 3 situations that happen to follow this shape. So the most fundamental place this guy comes from. So there's going to be a chi-square formula. There's going to be several chi-square formulas, the same way that there are several z-score formulas. And they all follow the same shape. So here is the most basic place that they come from. So if I took a sample and I find its S, how do I calculate the chi-square score for that? I plug it in this formula. How big was your sample? Multiplied by what you found squared, divided by the standard deviation of the population. You guys kind of with me? A little bit? A little tiny bit?
I think so.
All right, so let's do this. If I had, let's say I have a sample of 6 things. So 4, 9, 10, 11, 28. What do you need? More, Jeff? 29. There you go. Can you guys, and let's say that it comes from a population that has a standard deviation of, you can do it, Jeff. Can you do it, Jeff? Let's just say 10. Sure. Can you guys calculate the chi-square for that? So what you do, a lot of you guys right now are gonna, in your brain, you're like, you just told us what the shit that, and you want me to, all right, so here's the formula. Do you know sigma?
Yes.
Do you know n?
Yes.
The only thing you don't know is this. Can you figure this out?
Yeah.
Shit, yeah. What are you going to use? What are you going to use to figure this out? You can do it. You can do it. 1 var stats. Right. You're going to put it in the form in your list. This is what you're going to do right now. Remember 1 var stats? Does anybody remember second calc 1 var stats? It tells you x bar. You guys completely forgot. Oh my god. We did that in the last test. Or you did, hopefully. You put it into list 1. You put it into list 1, and then you do 1 var stats. You get stat, calc, one var stats. So go ahead and try to do that. Try to figure out what the S is. It's a freedom. Oh, Jack, what's up?
On the top of the 4, it says N equals 6.
Yes, it does, because there's 6 things. Right? So what are you going to put in the list? 4, 9.
That was a 17.
Triple. 4, 9, 10, 11, 28, 29. Has anybody gotten that standard deviation yet? Ooh, that's so neat.
Wait, isn't S
Sorry.
the standard deviation for the sample?
Beautiful.
And then R is the standard deviation for the population?
No, be real.
Oh no,
It's sigma.
R squared is...
No. Sigma. R is its own thing. We got to be careful. Careful. I don't know what that was. But this is sigma.
Oh, sorry.
Lowercase sigma. It's not bringing R. Right? It's lowercase sigma. Uppercase sigma, of course, is the E dude.
So then that's...
Sorry. So that's the population standard deviation. With me. Because how do you make a z-score? What do you compare your data point to? The population mean. So how do you calculate a chi-square score? What do you do with your sample? You compare it to the population standard deviation. So there are similarities between these two. They don't look the same, but this formula gives us this picture, and then I'm gonna have a chart, just like the z-score chart, that tells me where things should happen, what's the probabilities. So what are you guys getting? So your S comes out to be what? 10.6. Oh, yeah, 1.0. I like it. You guys got that? You guys see that? Anybody curious why I don't use sigma? Because the calculator gives me sigma. Because we know this is a sample. Okay. Everybody good? So then what's the chi-square? It's going to be n minus 1, 5 times 10.61 squared divided by 10 squared. Right, just plugging stuff in. N minus 1 is 5. S we just figured out. Sigma we knew. Just to do an example. So let's see, what do we get? I don't know. Anybody want to tell me? Anybody doing this?
56.18.
Say again?
56.18.
Something went freaky. Yeah, 5.629. Weird. 5 times 10.61 squared divided by 10 squared. Doesn't it make sense it should be like close to 5? Because what are these? These are almost 1. These are almost the same, aren't they? So the answer should be kind of close to 5. No? Are you guys doing all right? You guys are looking really confused. All I'm doing is plugging stuff in. Make sure you can get, I get 5.629. I think a few guys got it. Does it make sense that it should be close to 5?
Yes. Yeah.
Okay. Because isn't this almost 1 when you do, I mean, isn't this almost the same thing?
Oh,
But that's a little bigger, so it should be a little bigger than 5. Hey. Okay. Yes?
I didn't get...
Say again, sorry?
I didn't get...
Oh. So the peak happens to be close to n minus 1, so the peak should be a 5. So we're a little bit above 5. I don't know if you guys can see that because, yes.
Is it just a coincidence that that's like about half?
That what, say again?
Is it a coincidence that that's like about half of the
Totally. Yes. I see what you're saying. Yes. So let me give you this. This is the, I already told you, you had one more chart. This is the chi-square chart. What happens is that shape doesn't change the general shape, but for different sample sizes, the shape changes a bit. All right. So what's some differences between chi-square and z? You can't have negative chi-square. We talked about that earlier. It's got to be 0 at least, right? It's not symmetric, is it? Shit. You don't even know how useful that fact was with z-scores. Much like the T-chart. The T-chart, let me say this, the T-chart is not as detailed as the z-score chart. Because I'd have to have a z-score chart sized thing for each degree of freedom. Can I handle any alpha? No, we saw one earlier. I couldn't handle 12%. I couldn't do 0.12 with the T-score chart because it doesn't break it down that much. Z-score chart breaks it down way big time. You can look up any percentage I want to. You can find any percentile you want to, right? Yes? Maybe? No, do you remember doing that stuff? On the z-score chart, if I asked you to. Everybody look at your z-score chart. Can you tell me what z-score represents P62? It's a good review because you're going to get this kind of question on the final. Z-score, yeah.
Yes.
3.1 sounds too much. 0.31, that might be true. Because what do you guys get? What's the 0.62 is close to what? What's the closest you can get to 0.62? 6217? And that's for 0.31. All right. And why does it make sense? 0 would be the 50th percentile, of course, right? So to get to 62nd, it should be a little above 0. 0.31 is a little above 0. At least it makes sense. Like, it's not negative, of course, because it's more than 50%. Okay. Do you guys now understand? Could I have made that P11 and you would have been able to find it? P92. Could you find? Yes. P13. You can find it. Right? I can make it P15.72 and you can find it. So the z-score chart is really detailed. T-score chart, nowhere near. Z-score chart, you got a ton of probabilities. How many probabilities are there in a t-score chart? Just like 5, however many entries there are. I can't remember how many columns are. You guys start to see what I'm saying here? No? So t-score chart, why can't it be more precise? Because for every degree of freedom, things change. I'd have to make a z-score size thing for every degree of freedom, and I didn't want to give you like a volume of charts. We're looking at chart 27, subsection B. No, I don't. Okay. So, this chart is not going to be as detailed either because look at this, degrees of freedom, everything changes a bit. Why does that make sense? Because the degrees of freedom is in the formula, right? Okay, so what's our degrees of freedom for this problem that we just did? 5. I like it. So look at 5. And just to get a feel for how things are spread out, let me see if I can't And again, this can't be that detailed. But look at 11.071. So we got 5.62. Well, let's see. Let me back it up a bit. So 9.236. Let's see if you guys can read this. As 10% where?
That one.
Area to the right. This kind of. Is everybody kind of with me? I'm just trying to get into how to read this, and I want to have a little bit of a concrete idea of stuff. So what percentage is to the right of 9.236 for 5 degrees of freedom is 10%? You guys see what I'm saying?
Yes. So,
And what percent is to the right of 1.610? 1.610, what percent is to the right? 90%. Kick ass. We're not very far away from 5, so what percentage is to the right of ours? A little less than 50%. So this is not symmetric. We have different values. It starts at 0, there's no negatives. But I can use it in much the same way that we use the z-score chart. So let me give you an example. All right. So we got what they want from this business? No? Yes? No? Maybe not? Okay. So I could have a situation where I have a claim about a standard deviation. We haven't had that yet. And the reason we weren't able to do a claim about a standard deviation is we had a picture that needed one standard deviation to tell me how it was shaped. I didn't have anything about how these were distributed. Okay, so what if I said my claim is the standard deviation is bigger than, you could do it, Jeff. Yeah, what did we get? Yeah, standard deviation is bigger than 10. Let's say. And let's say alpha is 0.10. I like it. Stay with me. Does this feel very familiar? So far, I mean, we have a claim. I know it's about a standard deviation, but we have a claim. Which one is that going to be? There's no equal sign. So so what's this going to be? I like it. All right. Now watch. I really want this to make sense. The claim is greater than 10. So how many tail tests would it be? How many tail tests? Greater than 10. How many tail tests? One tail. Where? Up here. I like it. And alpha is 0.10. And I don't know if you guys catch on, I'm relating it to what we did over there. Right? You guys see what I'm saying? I'm saying I have a claim that sigma is greater than 10, and I took a sample and I got that. Is that enough evidence that sigma is actually greater than 10? Because my sample standard deviation is greater than 10, but it's the same thing as before. It's got to be like bigger enough. So what is that cutoff chi-square score going to be? Well, what percentage is supposed to be to the right of it? 10%. We already looked it up. Degrees of freedom is still 5. And it's the same thing we just looked up a minute ago. What's 5 degrees of freedom for the problem we were doing? 5.
Oh yeah, 9.
So 9.236. So what did we find? What was our chi-squares? I would call this chi-square star, but you know, it gets a little bit cluttered. But it's just like Z-star. We calculate, this is the score theoretically. This is the benchmark, what I have to beat. That's the score observationally. We actually saw that happen. What did we get? We got 5.629. Is that enough evidence?
No.
No. We didn't make it. That's the very first kind of thing coming off of what we were doing before that we could use this for. Just because now we have the right picture. I really want you to get a sense that the idea behind the steps that I would use doesn't change. It's just I got to use the right distribution. And for standard deviations, they follow this distribution. They follow a chi-square distribution. But I could do all the same. I could figure out where my rejection region is. I could look at the sample, calculate the chi-square star, see where it falls. I failed to reject. Right? So we did not find evidence to support our claim that it's greater than 10. It wasn't bigger than 10 enough. I guess I'm just trying to give you a feel. Now, let me say this. The reason I didn't say this earlier is because you might not have paid as much attention. We're actually not going to do hypothesis tests with this. Some of you guys look angry, but some of you guys are like, thank God. You're angry because you're like, why did you make me sit through that shit? Because I desperately want you to see this idea. Hypothesis test as an idea that connects all of its steps. Right? If you have means or percentages, you have to check and make sure you can use a z-score, a normal curve. If you have standard deviations, normal curve, you can't use that shit. It has nothing to do with how they are distributed. You need chi-square. But now, once you got chi-square, you can do the same shit. Steps don't change. All right, so we're not going to do a complete one. I just want to give you a little taste of how it would fit in. So here's what we're going to do. Let me take all this over. So we're going to focus on a problem because I think we've done enough hypothesis testing. And there's a little taste of how it really doesn't change that much just because you're using this chart instead of a different chart. It really doesn't. So let's do something different that's not quite as, well, some of you guys might call it horrific as a hypothesis test. This is just one flavor of chi-square formula. Same way that there's different flavors of z-score formulas, right? Here's another one. This is kind of really kind of cool. Let me give you an example here. Let's say that we claim that. All right. This is the example I have on the sheet, and I don't care. M&M's colors are uniformly distributed. Everybody with me? What does that mean? That when you open an M&M bag, you expect what? Same number of each color. I like it. Right? I've got where did I put you, handout? Oh, you've already got it. Where's mine? Too bad. Oh, there it is. All right. So let's go through this since we've already got worked out. So like you said, if the claim is that they're uniformly distributed, then everybody should have the same amount. So if I had 40, what is it? What did I even say? We take a bag. Oh, I tell you how many. So there's 42 total. Right? If you add up all the colors that we see 42 total. If they were, I don't know how many puberties I'm going to have. If they were uniformly distributed, and I have 6 colors here, right? How many should each color have? Well, 7. Does that make sense? There's 42 total. So anytime the claim is uniformly distributed, you take the total number divided by how many categories. Does that just make physical sense? How much does each color get if they're uniformly distributed? Well, you take the total divided by how many colors there are. That's how I got 7. 42 divided by 6 is 7. So here's what's expected, theoretically, if it is uniformly distributed. I like it. So what we're really testing here is, it's not going to be uniform, but how different is it from uniform? Is it close enough to say sure, or is it too far away? It's the same idea. So here's where things get interesting. And part of this should make a ton of sense. So here's what I see. Here's the observations. Here's what I see. This piece here should make a lot of sense. It should feel very familiar. When would it be 0? What would that mean if I got a chi-square of 0? Like there's, what would it mean if it was perfectly uniformly distributed? That would mean that these would be the same. So that would mean that observed minus expected would be 0 for every one of them. Which then that would be evidence that it really actually does perfectly follow a uniform distribution. So I'm going to calculate, well, how far off is what I see from what I expect? And I kind of do it in one step. This is sort of like when we did standard deviation. Didn't we have to square to get rid of the stupid negatives so that they don't always add it to be 0? So we could do shit. So I see the differences between what I expect and what I observe, and I square it. Then I need to make that relative to the problem, what I expect. So I take 4 divided by, I always divide by what I expect. That's sort of like a normalization step. So I can see relative to what I expected, how far off are these things. So would you say a difference of 800 is big? Not if I expected it in the millions. Do you see what I'm saying? Like, would you say a difference of 2 is big? No, but you would be wrong if I was expecting it in the 0.000